Okay, let's take a look at section 2.6. So in this lesson we will learn Euler's method, which is a numerical procedure used to approximate the solution of the initial value problem y prime equals some function of x and y with some initial condition. So we use Euler's method when we cannot solve the initial value problem directly. Okay, so let's look at the idea here. Okay, so let's recall the tangent line formula at, say, y of x0 equals y0. So we're assuming, again, the differential equation looks like this. So the recalling to find a tangent line is going to be y minus our y0. Then the slope of the tangent line is the derivative evaluated at our point. So it's our derivative evaluated at our point times then x minus our x0 point. So I'm going to call this x minus x0 now. I'm going to call it h. So let me do that. Okay, so I'm going to let h equal x minus x0. I'll explain why in a second. Then rewriting, so replacing this with h, and I'm moving the y0 across the equal sign. And now I'm actually going to call the y on this side, I'm going to call it y1. Okay, let's keep going. Okay, I want to draw a picture now, so I'm going to erase a few things and draw the picture. Okay, so let me erase a few things here. Okay, so here's a picture I've drawn. So here's the idea. So here's your initial value problem up here. So we have the derivative as a function of x and y, and we have our initial condition. And our goal is to approximate the solution curve at each of these x values. Okay, so we know from the initial value problem that the curve we're looking for passes through x0, y0. So you know this right here is on the solution curve. And we can then find the slope of the tangent line at that point. So say that's the slope of say that's our tangent line right there. We can then move along h along that tangent line. So we're assuming all these x's are equally spaced. So x1 is going to be x0 plus h. H is some small number. X2 then would be x0 plus 2h. Xn would be x0 plus nh. So let's approximate, say, y1. Well, that'll be the y value corresponding to x1. We're going to approximate that by going along this tangent line here. So we're going to go along at h, and then that value over there would correspond to h1. Sorry, I meant to say y1. So you can see then this is the formula to find y1. So you're traveling along the tangent line h. So that's how we'd find our y1. So this is not perfect. Let me just demonstrate here. Okay, so here's the idea. So suppose this was our solution curve, and this is our x0, y0. So that was a point. That's a point on the solution curve. So if I travel along the tangent line here, you can see as I travel along the tangent line, as long as my x1 is close to x0, the y value along the tangent line will be close to the y value on the function. It's not perfect. That's why we need to choose our h value to be small. Because if you chose your h value to be very large, so say your x1 is way over here, say, you can see the tangent line and the function aren't necessarily close anymore if you choose your h value, just to be a large h value here. But if you choose the x1 value very close to x0, then the y value on the tangent line and the actual function value will be very close to each other. Okay, so that's the idea. So up here, moving along the tangent line, if h is small, this y1 should be close to the actual function value at x1. So let me write that. So the y1, our approximation along the tangent line, is roughly equal to y of x1, so y is our actual solution, say, when the absolute value of h is small. Okay, so therefore this y1 should be a pretty good approximation if the h value is small. Okay, so for our next approximation then. So for our next approximation, we'll be taking the y1 value. Okay, and we're looking at the slope of the tangent line at x1, y1. So say here's the slope of the tangent line there. Say that's the tangent line. We're going to move along at h again to get our approximation for y2 next. Okay, so y2 would be there then. So pretty much it would be moving along tangent line. So I'm just going to, I could rewrite this now, and just in place of x0 I can write x1, y1, y1, then it'll be y2 here. Let me write that. So that'll be the formula for y2. And you can probably see a pattern starting to emerge. So for my y3 then, well, my y3, say, we're looking at x2, y2, looking at the tangent line. So say the tangent line is there or something. So I'm moving along that, and I give my y3 value. So y3 value would be here, and then so just moving along this tangent line there. So it's just going to be like this formula here, just replacing y2 with y3, x1 with x2, y1 with y2, and h will just be with h. So let me write it here. So we get this done. So in general then, we could just say y to the n equals y prime of x to the n minus 1, y to the n minus 1 times h plus y to the n minus 1. So let me write that here. Okay, so in general, y to the n will be equal to y prime of x to the n minus 1, comma, y to the n minus 1 times h plus y n minus 1 subscript. Note then, again, these are just approximations, so the y of n will be approximately equal to y of x of n, where y here is the actual solution that we're trying to approximate. So this is Euler's method. Okay. All right, so this is Euler's method. So let's take a look at an example now. Okay, so here's our example. It says that use Euler's method with h equal to 0.2, y1 equal to 2, and our y prime equal to 2x plus y squared to approximate y of 1.4. Okay, so let's recall Euler's method here. Okay, so here's Euler's method. So pretty much the yn is approximately equal to y of xn, where y is the solution. Y is the solution curve we're trying to approximate, and xn is equal to x0 plus n times h. In our case, the x0 would be 1, and the y0 would be 2. So let's figure out what the n value would be in our case. Well, we're trying to create the 1.4 here. So the h is 0.2, the x0 is 1. So let me solve this then. Alright, so to find n, we'll have our xn, which is 1.4, equals x01 plus h times n. Okay, so let's subtract 1 on both sides and divide by 0.2 then. So doing that we get, so solving we get then n is 2. Okay, so Euler's method is actually a recursive formula. So it means in order to find yn, you're going to have to know yn minus 1. So in particular, we're going to have to find first y1 and then y2. Okay, so let's first find y1. So here's my y1 formula here. Okay, and as we already mentioned, the x0 is 1, the y0 is 2, so let's plug those in, and the h is 0.2. So making the substitutions, we then have y prime of 1, 2 times 0.2 plus 2. Now y prime is given by this formula up here, so we're going to put 1 in place of x, 2 in place of y here, and work it out. So doing that we get then Okay, so again I put 1 in place of x, so it'll be 2 times 1, 2 in place of y, so it'll be 2 squared times my 0.2 plus 2, and working this out then at 6 inside there, so right over here. So I get in 6, so y1 is 6 times 0.2 plus 2, so working this out you can check it equals 3.2. Okay, now let's find our y2 next. Okay, so our y2 then will be y prime of x1, y1 times h plus y1. We just found our y1 was 3.2. Now our x1, we're going to have to use this formula up here. So let me just write our in general formula here. So in general then, our x0 is 1, our h is 0.2. So this is how we find our xn. So in particular, let's find x1. So x1 then will be 1 plus 0.2, so it'll be 1.2. So that's what I'm going to use for my x1 here. And my y1 I'm going to use 3.2. So doing that we get then. Okay, so we'll have our y2 then will be y prime of 1.2 comma 3.2 times 0.2 plus 3.2. Again, the 3.2 is the y1 and the 1.2 is the x1. Now I'm going to have to put these values into my y prime up here. So I'm going to put 1.2 in place of x here, 3.2 in place of the y here. So doing that we get then. So plugging in. So again we're going 1.2 in place of x here, so it'll be 2 times x plus y squared, y is 3.2, times my h 0.2 plus my y1 3.2. So let you check when you work this out in your calculator, you get roughly equal 5.728. Okay, now we're just about done, just make some observations here. Okay, so note that x2 then will be, so plugging into a formula up here with 2 in place of n, it ends up being 1.4. So then we're using this formula that y to the n is roughly equal to y of xn. So this is my y2 is going to be approximately equal to my y of x2, but x2 is 1.4. So therefore a y of 1.4 should be roughly equal to 5.728. Okay, so we've used Euler's method to approximate y 1.4. So that's our answer there. So we're done. Okay, so I'm going to leave the video here.